Thank you so much for the introduction, and thank you, the organizers, for this conference, for the opportunity to speak. And this is my joint work with Jason Green. And I will speak about fusion categories in characteristic 0 over complex numbers, which of course is very pedestrian, given the scope of this conference. I mean, my only excuse is that what I'm going to say is relatively new, at least to me, and you need to start somewhere. So we'll start with that generality. So what it is all about? So, well, there is a general, thing in algebra when you try to decompose algebraic object into some parts. For instance, like you decompose Lie algebra into its solvable radical and semi-simple quotient, right? Or you factor out like an algebra by Jacobson radical. So something like this can be done with fusion categories. Decomposing braided fusion category. Now, what this usually amounts to is to somehow separating group theory part from non-group theory part. Okay, so I'll make it more formal. But before doing this, I want to introduce some tools that I'm going to use. So there are two general constructions. Oh, yes, and the relation with symmetric categories of what I'm going to talk about is this. Now, I think people would agree that groups and supergroups are not meant to be studied in isolation. They're meant to act on things, right? So on the level of categories, this amounts to placing a symmetric or Tannakian category inside a larger category and checking how it sits there. All right, so that's what I will be concerned with. So the two constructions are the following. The first construction is localization. So what is this? So a given braided category C, consider a Tannakian subcategory E inside C. And let's consider this. It's called the centralizer, but it's really an analog of an orthogonal complement. It's the category, full subcategory of C consisting of objects X with the property that the double braiding of X and V is identity for all V in E. So it's called centralizer. So what I mean when I say that that's an analog of a orthogonal complement is the following. So you can take an abelian group with a quadratic form Q. You can take a subgroup E of A, which is isotropic. And so this orthogonal complement is the analog of this thing. Okay. All right, so now what do we do then? So we can form a new category. We can tensor E prime. Now, E prime is, of course, contains E, right? Because E is symmetric in particular. So you can take tensor product of this orthogonal complement with vector spaces over E, where the category of vector spaces is a module with respect to the fiber functor, right? So note what matters here is not the fact that it's E is a representation of a group, but representations of a group, but the fact that there exists a fiber functor, right? So in this sense, this construction can be generalized, but I only need this generality. So that's what is called localization. It's again a braided tensor category where we somehow chop away, the Tannakian part from it, the chosen Tannakian part. On the level of metric groups, it's just taken the quotient of orthogonal complement of E by E. Now, there is a construction in the opposite direction.
So this is,
There is construction in the opposite direction called gauging. So, so here is what we do. So here we sort of start with this thing and are trying to enlarge it to construct a larger category which contains a Tannakian subcategory inside it. So the way it works is as follows. So here I will need a group. So given a group G, and let's say B braided fusion category, what we do, we construct, well, suppose we manage to construct a monoidal two-functor to the two-categorical Picard group of B, which is the categorical group of invertible B-module categories. Okay, so there is an operation of tensor product over B similar to how one can tensor modules over a commutative ring. Now, from this data, one constructs a certain G-graded extension of B, where here G is mapped to BG. And then one takes equivalentization of this. So what one obtains is a braided category that contains Tannakian subcategory rep G inside. Okay, so these two constructions are inverses of each other. If you repeat them, you will end up with the same data. Why, Vita?
I think in first construction you want to get crossed category or something.
Well, you will get crossed category if you take C here instead of a prime. This way.
I mean, so I just want these constructions to be inverse to each other.
Yes, so this is the inverse is between like the following sets of data. C with rep G sitting inside, right? And the other piece of data are just monoidal two functors like this, okay? Oh, good. Okay, so, all right, so they're inverses of each other. Okay, so now, so for example, to give you a right intuition about what's going on, for instance, a gauging, the trivial case, the gauging of the category of vector spaces is the representations of the twisted Drinfeld double of a group. Okay, so it's already a rather non-trivial thing. And of course, it's interesting to take more general categories here. Okay, so now one can use these two procedures to construct certain invariants of a braided fusion category, and one of them is the core of braided fusion category. So what one does, let's give it a name, let's call it B. No, I called it C before, so maybe I should stick to it C. What one does, one takes E to be maximal Tannakian subcategory of C, and do this localization. Then the resulting category doesn't depend on choice of E. The thing is this, a given braided fusion category can have many different Tannakian subcategories inside, right? And it doesn't matter which one you take, the result is the same. So this is invariant of C. And it's quite useful invariant, but there are limitations because this whole thing does not depend on the choice of E, but there can be non-equivalent maximal Tannakian subcategories. Okay, so for example, invariant of C, but the equivalence class of E is not. To illustrate, the difficulty here, let me just point that it's quite possible that one has braided equivalence like this for different groups G and G prime. Okay, even if the corresponding Trika cycles are identical. Okay, so you cannot really associate a group to this data. Why, Vito?
I don't like that omega equals to omega prime, like cycles in different groups.
Fair enough. Okay. All right. Okay. And now you see, like this question is, it's an important question also because equivalence classes of twisted representation categories of twisted Drinfeld doubles, they parameterize Morita equivalence classes of group theoretical categories. So now one can actually find necessary and sufficient conditions for two such pairs to produce equivalent categories, but it's not really a parameterization, just like describing the set of all equivalent pairs. Okay. All right.
Sorry, I didn't get the last thing. So you say you can parameterize for Morita classes of group theoretical just with twisted doubles of groups?
Yes. So like the equivalence classes of such things, braided equivalence classes, are precisely Morita equivalence classes of these things. Okay. So, but like I said, G is not an invariant of it. So what is an invariant? So one can do this. So let's again start with C braided fusion. Now, most of the time I will consider braided categories that are non-degenerate. It's not necessary, but it will be convenient. So I assume non-degenerate means that there are various definitions. So one of them is that the only object X that has like this double centralizing property with respect to every V is a multiple of the identity object. Okay, so now maximal Tannakian category is not invariant, but their intersection is. So let's take intersection where E and C is maximal Tannakian. And we will call this thing the radical, or Tannakian radical of C by analogy, with how radical is defined, how Jacobson radical is defined in algebra. So Tannakian radical. Now, because it's a Tannakian category itself, this Tannakian radical is equivalent to the representation category of some group G, G sub C, and this group is now n invariant of the braided fusion category in question. So, for example, so again, let's take the simplest example. Let's take representations of the Drinfeld double of the group. So let's that be C. Then the radical of C, well, it's necessarily a quotient, representations of a certain quotient of G, and this will be representations of G by Ng, where N G is generated by all normal abelian subgroups of G.
And what are maximal Tannakian subcategories there? Do you know what?
Well, there is a parameterization, but again, they are parameterized by certain data that involves a normal abelian subgroup and the G-invariant bilinear form on it. Okay, but this is beyond my point because I won't be interested in them individually. I'm interested in their intersection. Okay, so note that this group is necessarily nilpotent. So it's a canonical nilpotent subgroup of G. In the case of the twisted Drinfeld double, you can still produce this, but there will be some cohomological conditions. So, well, maybe I'll write this down. So the radical of the representations of the twisted Drinfeld double is the following quotient. I'll call it an omega, where this right here, an omega is generated by all normal abelian subgroups of G, such that trickle cycle omega is inflated from this quotient. Okay, so it's rather a neat description. So we have this invariant. Now, we will be interested in a class of such categories where this intersection is trivial. So by definition, we say that a braided fusion category C is primitive if its radical is trivial. Okay, so now, so for instance, now this category would be primitive if G is generated by its normal abelian subgroups. So this is stronger than just being nilpotent. There are nilpotent groups that do not have this property. Okay, so all right, now because radical is an invariant, then the corresponding localization. So the that's a separate definition. So the localization of C with respect to its radical, we'll need to give it a name, and I will call it a mantle of C. So let me explain the reason from this name. It comes from geology, which makes this talk truly suitable for pure and applied mathematics. So this is, let's say, pretend this is our Earth. Then there is the core of which I already introduced, right, which is a very hot. Well, I guess it should be yellow. Then so this is the core, and then there is the stuff around it, which is not as hot, and I think it's solid. I mean, there is a geology department nearby, if I remember correctly, just like right across the street. We can ask, and then the rest I think is called the crust. Crust, mantle, and that's core. Right. So the idea is that it's kind of larger than the core, right? But still very hot. Yeah, go ahead.
It's an invariant, so you wanted to call it just a mantle, not the mantle?
No, it's there. I mean, sorry, that's my English. Yeah, so the okay. Yes. Right. So you are here. Okay. So again, I don't. I mean, like for instance, with name primitive, you have an analogy in algebra. With this, I couldn't come up with a meaningful analogy. Okay. So we'd like to investigate this invariant, and so in particular, let's see. So how can category be primitive? Well, there can be like two two extremes for two extreme reasons when it's primitive. One is that it has like too many Tannakian subcategories, and another is that it has none at all. Okay, so we are going to consider these two properties separately. So given primitive C, what we can do, oh, by the way, so I should say here that because a primitive category is necessarily non-degenerate or slightly degenerate. It cannot have, a Tannakian part in its Mueller center because it would contribute to the radical, right? So such C is non-degenerate or a slightly degenerate. Slightly degenerate means that the Mueller center is the category of supervector spaces. So given primitive C, let's consider...
Question. So a mantle doesn't have to be primitive?
Mantle is primitive. That's
Mantle is
yeah, okay. So now that you mentioned it. Yeah, so I should say like the theorem.
But it's not completely obvious, right?
There is an argument, but it's not hard. So the theorem, I mean, again, it's along the same lines that, that the quotient by radical is semi-simple, So theorem that, the mantle of C is primitive. Now, in fact, there is more to it, okay? So the radical acts on this mantle, but it acts in a kind of in a special way. It doesn't really create, new Tannakian subcategories. All right, so there is a restriction as what action can be there. Okay, so, but I wanted to define this. So, given
You mean not the radical acts, but the group corresponding to radical?
the group, yes. Yeah. So, given primitive C, so let C set, where a set is for saturated part of C, be the subcategory of C generated by all Tannakian subcategories. Now, of course, it doesn't have to be Tannakian, right? Two Tannakian categories do not have to centralize each other, so whatever they generate is braided, but not necessarily Tannakian. Now, this saturated part is itself primitive for the same reason, so also primitive. And so, as we observed, it's either non-degenerate or slightly degenerate. So in the favorable cases, let's say when C and C saturated, so if C and C saturated are non-degenerate, then you would have a decomposition of C into the product of saturated part and anisotropic part. I don't know how to call it, like so C anisotropic. Anisotropic means that there are no Tannakian categories other than the trivial one. No Tannakian subcategories other than VEC. Well, they don't have to be both non-degenerate, but for instance, they can both be slightly degenerate, or one of them slightly degenerate, another non-degenerate. In these cases, there is also a version of decomposition, but you will tensor not just as a Deligne tensor product, but as a product over a SVEC or things like this. So I don't want to burden you with technicalities, but there is a way to decompose it like this.
And this is analogous to the corresponding decomposition for quadratic forms, right?
That's right, yes. Well, again, like issues like if this is a two group or not two group, so. Yeah, so this is somehow like a good part, which, I'll talk about, and in particular, this is nilpotent. But this is kind of difficult part, okay, because, in a way, both parts are difficult. So we know that classification of finite groups is difficult, okay? Well, at least we kind of have a general idea of what they are. With anisotropic categories, it's worse. We kind of know it's difficult, but we don't know what the classification is.
And what is the relation between this anisotropic part and the core?
Anisotropic Well, the core doesn't have to be anisotropic. It's, I think so what's the right way to say? It's kind of weakly anisotropic. It doesn't have Tannakian subcategories other than weak, which are stable under the group of autoequivalences. Does it make sense? Yes. So, so I would imagine this part is kind of probably like a further localization of the core or something like along these lines. Okay, so this category nilpotent, and in particular, now nilpotent braided fusion categories are known. They come from group theory. Okay, so this one is group theoretical, and the integral in particular. So, and it can be obtained from the representations of a Drinfeld double of a nilpotent group after some manipulation. So if you understand nilpotent groups really well, then you understand these things.
Yeah, just a second. So anisotropic category is smaller than the core? Like dimension is smaller or equal? Is that what you claim?
I mean, it can, well, so what I said is that it cannot coincide with the core.
May not coincide.
May not coincide with the core. I did not really think about comparing their dimension. Note that this whole thing is actually, under these assumptions, So, it may fail, and then, this thing is not like anisotropic, but something else, okay?
But this, you said that this only gives a factor of 2 or something?
Well, what I said is that, like, if this non-degeneracy fails, you have to accept the different kind of decomposition. Okay, so I don't think there is a direct relation between the two. So, so for instance, it can happen that the core is like a hyperbolic, category, ZP plus ZP, right? But it's not anisotropic in any way. Okay, so, all right, so, but let's talk about this more. So let's talk about the situation that we do understand. So it's a reasonable question, once we have this notion of a primitive category to try to understand it in the simplest case, so like primitive metric group. So here the metric group is an abelian group A with non-degenerate quadratic form Q by an old theorem of Joy-Allen-Street. These are the same as pointed braided non-degenerate braided fusion categories. Okay, now because it's nilpotent, it suffices to consider P groups, okay, with this property. So as it happens, situation is easier when P is odd. So if P is odd, then a metric group, metric P group A is either saturated or anisotropic. Now, anisotropic anisotropic P groups, of course, are known. These are generators of the Witt group, right? So those are known. And so what would be the saturated then? Well, there is a characterization of this. So a metric P group is saturated if and only if, so let me write this down here. So proposition A is saturated if and only if it has a hyperbolic sum of the maximal exponent. So let me put it like this. So there is so A contains like Zn cross Zn hat, where n is the exponent of A. And this is a metric group with the usual, quadratic form. Makes sense? So there should be like more than one summand for sure, right? And furthermore, like the summands of the highest order, the two of them should form like this hyperbolic pair. Okay, so which is how?
You are really saying that if something is not anisotropic, then it is automatically saturated?
No, this is something that doesn't look right.
Well, it can be neither. So by a metric P group, I'm sorry, I missed here adjective. So is primitive. Sorry, is primitive. If thank you for this. Yeah, otherwise it makes no sense. Of course, thank you. So, all right. I mean, that's what I was saying. This we want to classify to describe our primitives. Okay. So well, this is something that's very easy to check in practice. Now, if P is equal to 2, then the situation is more complicated. Then, so a metric P group is primitive, then in fact there are like 3 possibilities. If sorry, not if then. Well, implies that either A is saturated, or A is anisotropic. Now, the characterization for saturated is a little bit more involved than that. So in addition to this, you want to, so as above, plus what you need to have is that your quadratic form is a diagonal of a bilinear form, which is automatic in odd case. Okay, but is not in the 2 case. So plus Q being diagonal. Anyways, the point is that there is a transparent classification, or it can be mixed. Or it can be mixed. So it can have like, a saturated sum and an anisotropic sum. And to give you an example of this, consider, for instance, this category, so representations, the center of rep Z2 plus SVEC, right? So it's saturated, right? But I mean, it's what I'm trying to say here. No, this one is saturated. Well, what I mean by this is that it would decompose in the sum of something saturated and something anisotropic, but not necessarily uniquely. Okay, this is the best I can say, but they can all be described. Now, next thing I'd like to talk about is, okay, so what we did, we assigned this invariant to a braided fusion category, right? So we assigned so let's list the things that we did. So to C, we assign its radical, which is just representations of a certain group. We assign the mantle. So this is Tannakian category, subcategory group. We have a mantle of C, which is a primitive braided fusion category. And of course, the key thing, of course, is this action of this group on the mantle, which kind of determines the whole thing. So this we have, and which is, of course, the heart of the matter, but also the most difficult thing. It's just a monoidal two-functor from G to the IPAM group of the mantle. Okay, so now what we'd like to do is to axiomatize such things, okay? Because not every functor will appear, All right, the condition is that the radical is the intersection of maximal Tannakians is strong, right? So we will try to axiomatize this invariant. Okay, in other words, describe really which f can appear. Okay, so
So just to clarify,
yeah, go ahead.
proposition. Yeah. So I understand that. Do I understand correctly? So metric group has this light form, which is the set of elements which square to 0, and saturated means that light cone spans the group.
What do you mean square root to 0? I'm sorry.
Q of x equals to 0.
Q of x, okay. Yeah.
Fluid with themselves.
Yes.
And the light cone spans the group, and so that's why this proposition kind of is natural.
That's right, yes, yes. Okay, so we axiomatize this invariant. In other words, we want to figure out what properties of f, the relevant properties of f. Now, well, so informally, I mean, it's kind of useful to refer what I was saying before is that so remember that like when we started like with this rep d omega g, then the relevant property was that we were looking for normal abelian subgroups from which this omega can be inflated, right? So normal abelian subgroups from which omega can be inflated. You see, if there are no such subgroups other than the trivial one, this category is primitive. Okay, so we'd like to say something like this in general case, but and so I'll try to come up with this. So informally speaking, we will need functors f that are not induced from anything like smaller, in a sense, that are primitive. So let me. I'll come up with this definition. So n in primitivity datum for this functor f from G to a pk of a braided fusion category is the following. So is the following collection. So n in G normal abelian subgroup, E inside B is a Tannakian G-stable Tannakian subcategory such that there is a sub-extension, so let me write down. So EX, where X in N, inside CX, where, sorry, what is B? BX, where X is in N. So this is a graded extension of B, okay? So suppose the trivial component has a Tannakian subcategory, and furthermore, this Tannakian subcategory is part of an extension, okay? Well, this is a strong condition that may or may not happen, okay? So in this case, you can just think of this as following. So this extension is induced from this extension. If you tensor it with the trivial component, you'll get this, okay? All right, so the extension of B is induced or inflated. I'm not really sure which would be the right term here, from extension of E. And furthermore, so what one needs to do is that this extension here is G-stable with respect to the action, and the action of G factors through the quotient map from G to G. Okay, so again, I don't know how to kind of pack this condition in, like in a more presentable form, but I hope like the general meaning of it is clear, like so it's induced from something simpler. Okay, so in particular, if it happens that your group G has no normal abelian subgroups, or if they act sufficiently non-trivial, then this is a good thing. Okay. Now the consequence of this axiomatization is that, of course, now.
So the implication is that we don't want to have this primitive.
Yeah, that's right. So I have to finish, right? So the property of C that we are looking for is that C so we consider triples like this, like C, B, F, where G. Okay, so where B is primitive and F has no imprimitivity datum. So we might as well say that F is primitive in this sense. Okay, so and any G can occur. It's just like not G itself, but how it acts, is essential. So such triples then they parameterize braided fusion categories. Okay. Again, of course, like we don't, like I pointed here, so we don't really know all primitive categories. There is a black box or two black boxes, if you will, one for anisotropic categories, another for like finite groups. So black boxes all around. But what can be done? So if so this thing is the mantle. So if mantle is sufficiently small, then you can actually compute everything. You can compute all possible functors, you can compute the Picard group, and so on, right? So this opens the door like for possible classification of such things. So for example, let's see. So if mantle is trivial, so if and only if, let's say B is non-degenerate, so then B is the twisted Drinfeld double, where G has no normal abelian subgroups. I don't know if there is a term for such groups, such that omega belongs to the image of the inflation map.
So do I understand correctly that the idea is the following? So like in all your old paper with Drinfeld and Vita and Shoma, you had this procedure of cutting down braided category, by saying taking core and then again taking core and then again taking core.
But I mean,
until you stop.
But I mean, you cannot do this forever. There are no this like Russian dolls, like that.
Yeah.
But you can only do this twice, like things like that.
Twice.
Yes, at most. Yeah.
But this
Russian dolls come forever?
Huh?
Russian dolls come forever? Oh, okay.
You will be amazed. Okay.
Yes, but this is a way to do it in one step, basically. What you are proposing.
Well, no, I don't think it's that, because like this kind of goes in a different direction. We take a core and then we take the core of the core.
Yes.
And the result in our paper is that's it. You should not take the third core. But now the mantle, look at this picture, So this is the core, like you take like a subcore. But this is the mantle, we take like
No, but I mean this anisotropic. So how is that, maybe my question should be, how is an isotropic part related to the second chord? Is this, maybe it's more related to that.
I need to think. I cannot answer right away. So, yeah. Okay. So like it's that, and so now, well, for example, if let's say mantle is anisotropic, then I mean, of course, the generalization of that. So we would have like categories B, which is obtained from this functor. So from G, this functor, pick B. So it should not. Now, I mean, it's not right to talk about the kernel of it, right? But let's say we do, then no normal abelian subgroup of that, other than trivial one, is in the kernel. So this does not factor through G mod n. N is normal abelian. Yes, but in general, of course, like so, if you have some interesting mantle, then you have to compute the Picard group and then consider functors, such that normal abelian subgroups of G act rather non-trivial. Like say, if they act free, that would be sufficient. Okay, so it's the condition I cannot really comprehend completely, but at least it's something that can be stated. Yes. So also, I don't know. I mean, there are equations that are purely group theoretical here. So, for instance, like which nilpotent groups have this finite nilpotent groups have this property that they are generated by normal abelian subgroups. So with JSON, we did some numerical, calculations. It appears that the proportion of this group, percentage of this group kind of decreases, like with the class of this group, or with nilpotency class of that group. So fewer and fewer of them.
What is easiest example of group which is not generated?
Dihedral group of order 16. Yeah, so all those of class 2, of nilpotency class 2, will have this property. Yeah. Okay, so that's all I had to say.